Hello, everyone. Welcome to our second part of Lecture 4. I hope everyone is having a good week, that everything's going well. As always, any questions, concerns, or issues, please reach out. Either send me an email or just come into my office hours. All right, so today we are, just a quick reminder, quiz number 1, open Monday. So you have until Sunday, 11:59 to get that done. So please make sure to do that. Has a 45-minute time limit. Must be done in one sitting. So just make sure to get it all done. Set yourself enough time to finish it. And second weekly lecture reflection will open up today, Wednesday. And as usual, will be due Friday. Okay, so moving on to our lecture. So last week we introduced sensation and perception. And today we're going to be discussing our theories of pattern recognition. So just a quick review from the last lecture. So we discussed sensation and perception and how sensory information is received and interpreted to actually form perceptions of the world, and how none of it's actually, quote, real. We're perceiving it as how we perceive it. We also talked about our top-down and bottom-up processes. So how raw input, bottom-up, and prior knowledge interact in perception. And then we talked about our dorsal and ventral pathways, our what and where pathways, and that these are separate, distinct neural pathways responsible for identifying objects in the environment and then locating where they are in the environment. Just a quick question, maybe pause and think about it for a minute. So how do you think pattern recognition might build on what we've already discussed, especially top-down and bottom-up processes? So maybe pause and take a moment and just think over how you think bottom-up and top-down processing might work or interact in recognizing patterns in the environment. All right, so hopefully you've paused and thought about it for a minute. So let's introduce pattern recognition. So what is it? What is pattern recognition? Well, it is our brain's ability to identify and categorize objects and patterns within our environment. So we talked about sensory information. That's all the stimuli that we're being bombarded with all the time. And our brain is constantly trying to make sense out of it. And it's trying to make sense out of it by finding patterns within it. And it's fundamental to all cognitive functions. Without pattern recognition, we wouldn't be able to do much of anything. This is how we make sense of the world. We make sense of the world by recognizing things that are familiar to us in our environment. You can imagine what life would be like if you didn't do this. It would be impossible. So pattern recognition is fundamental to our ability to navigate the world and function. So as I noted, it's critical in just daily function. This is how we recognize people. This is how you recognize your parents, your friends, your pets. It's how you recognize everything in the environment, is using pattern recognition. This is how we get through the world. We use it to navigate. If we didn't have the ability to recognize patterns and use them as spatial cues, we wouldn't be able to move or go anywhere. And this is also how we read. Reading and interpreting language, it works via pattern recognition. So this is, again, it's fundamental and at the core of all of our cognitive abilities. And most importantly, not most importantly, but importantly as well, is that it enables us to respond quickly to our surroundings. So as we've talked about before with bottom-up processing, how that's more cognitively demanding than top-down processing, how you have to build everything up before you know what it is. Pattern recognition is almost like a cheat code where we're looking at something in the environment and we're recognizing patterns in it and using information we already have stored in our memory to identify it. So this allows us to respond much more quickly to stimuli than if we just had to build it up from the bottom. So how does it work? Well, we have our good old bottom-up processing. So this is, if you look at the figure on the right, starting with the bare essentials. So you start with processing the features. So what are the features of the stimuli? That's bottom-up processing. And then we move sort of upward in this image until top-down processing is integrated as well. And this can change depending on what the stimuli is. Sometimes bottom-up processing is more necessary. Sometimes top-down processing works quicker, but it works by first identifying whatever the features are. So in reading comprehension, you identify the actual letters themselves. You process those letters. So what letter is it? You then move on to processing the full word itself, then on to the phrase, and then you comprehend it. So comprehension is sort of the end of this the end step here, which is top-down processing, comprehending the information that's been built up from the bottom, from the features themselves. And when we talk about how pattern recognition works, as I've noted earlier, and I keep trying to hint on in this class, the role of memory, how memory is critical in all that we do as well. And within pattern recognition, memory is a critical component. And then our long-term memory, so this is all the information that we have stored in our brains from all of our prior experiences, this allows for that really quick recognition of familiar objects. So when you're scanning your environment, you're identifying objects in the environment, you're recognizing patterns, and then using your long-term memory to identify them. So again, you can imagine what it would be like if you didn't have any long-term memory of anything. So imagine being dropped onto an alien planet where you don't know what anything is. You've never seen anything there before. You have no memory of anything. It's just all new. Your memory would not serve you then, and you'd have to just be building everything up and trying to identify what it is. And you would not be able to do much of anything else. So in addition to the long-term memory, enabling pattern recognition to happen much quicker, short-term memory is critical as well, in that this is where that incoming sensor information is being briefly held so that you can work on that information. And when I say work on that information, I mean actively think about it, trying to understand what it is. And memory and perception interact with each other. So when we have a memory for the item, when we have some kind of prior information, as I noted, pattern recognition happens a lot quicker than it did if we did not have it. So if the information that's incoming matches something that we have stored, matches a stored pattern, we will perceive it much quicker than if we don't have that already stored. All right, so that's our introduction to pattern recognition, what it is, how it works, the important role of memory in pattern recognition. So let's now talk about our theories. We have three that we'll discuss. We have template matching, feature detection, and recognition by components. And for each theory, we'll define what it is. We'll talk about how it supposedly works. We'll talk about strengths and weaknesses. And we'll also just briefly discuss what roles bottom-up and top-down processing may play within that theory. And I'll just note, if you're hearing an odd sound, I don't know if it's being picked up at all by the camera, but one of my cats is sitting here next to me and I think has like a world record for purring level, the amount of purring, the loudness of it. So if you're hearing a strange noise, that's my cat purring. All right, so let's start off with template matching theory. So as the name states, template matching theory suggests that for every object, everything that we encounter, our brain is storing a template of it. It can only do this once we've already encountered it. So we encounter something, identify what it is, and then our brain stores a template. So just think about that for a moment, if that makes sense to you. If you think the brain works that way, do you think the brain is capable of this, of holding and storing a pattern for every single thing that we encounter in the environment? How does it work? Well, it suggests that when we perceive a stimulus, the brain is what it's doing is it's trying to match that stimulus with one of these stored templates. So you have a template stored in your brain for an electric guitar. And you go out to the record store and you see an electric guitar, and your brain is trying to match the one you're looking at with the one that you have a template for. And then that's how it's identifying it as an electric guitar. So a good example would be recognizing the letter A by matching it to your brain's internal template for an A. What is evidence for this theory? So let's talk about a study, one of the early studies, where they actually investigated this and tried to determine the role of template matching. So this was 1974, where Phillips, this is the last name, they investigated whether people could rapidly match patterns based on templates stored in their short-term memory. And to explore the role of template matching in recognizing visual stimuli. And I'll just note here that we'll be discussing visual stimuli in this lecture today. Again, we have all the different modalities, auditory, olfactory, so on, but we'll be sticking with visual. So the methods were, their participants, they were shown two different visual patterns. So we have two groups here, two groups of participants. They were shown two visual patterns, grids with randomly filled squares in quick succession. We'll actually run through this, so you'll see what those look like in just a moment. And the participants were tasked with determining whether the second pattern was identical to the first. So our two conditions were the no shift condition. This is where the patterns were presented in the same location with no spatial shift. The shift condition, the second pattern was shifted either slightly to the right or the left. So what they were doing is they were trying to understand whether participants who were shown these two visual patterns, whether or not the template mattered. So is it in the same place or a different place? So let's actually walk through it. It'll be easier to sort of walk through it than explain it. So during the demonstration that I'm going to run through, there's going to be a star that will appear on your screen. So focus on that star. As soon as that star disappears, you'll see a pattern for about 1 second, followed by a blank slide, and then quickly another pattern. Your job is to determine whether the second pattern is the same or different from the first pattern. Okay, let's do it. So this is the shift condition. We'll do the shift condition. So the other condition, well, you'll see. All right, so here we go. Oh, I'm sorry, let me run through it again. I'm sorry here, it's not working correctly. The star is not showing up on the main screen here. I apologize. I've got it on the other screen, but just not this one. Okay, let's start it over again. So there's your star, so focus on the star. All right, so I apologize. That didn't quite work as it was supposed to. For some reason, it didn't work as well on the main screen. Here's the second screen. But essentially what the experiment did was it had the subjects focus on the star, and then it flashed this on the screen, and then it flashed this on the screen, while the star is there the whole time. And then off to the right, it flashed it over to the right. So the first two were on the left, the second one was on the right. And for each of the first two conditions, so the first two squares, the pattern appears in the same location. And the idea is that this allows you participants to use the visual information stored to compare the different patterns. For the third set, the position switched, it was moved. And the idea is that the patterns are identical for the first and third conditions. They're different for the second condition. And that the pattern switching over to the right is what prevented people from noticing whether it was different or the same. So the run through didn't quite work as I intended, but let's just walk through the explanation here. So in the no shift condition, this is where the square appeared in the same place every time. The participants pretty quickly and accurately determined whether the two patterns were the same. And this suggests that people can quickly match the second pattern to a stored template of the first pattern. So because it's in the same location, they have a template for that pattern. Second one appears, it's in the same spot, and they can quickly match it with that template they have stored. In the shift condition, the one that we tried to walk through, performance decreased quite a bit. So participants were far less accurate when the patterns were shifted. And this suggests that when the second pattern was not in the same location as the first, participants could not match it to their stored template. So what it's saying is that even having this little shift in where it showed up, this interrupts or disrupts the ability to use template matching. So as we'll see, that's a weakness for this theory. So let's think about some. So what are some issues that stem from relying on templates? So if this is what our brain's doing, using templates to recognize information objects in the world, what are some problems with it? Well, you can imagine one, which is that this requires that the template be in the same position and same orientation every time, and the same size as well. And this is not how the real world works. Things are often in different positions, different sizes, different shapes, different orientations. So if we have a template of, a 6, and we see it upside down, if we're using template theory, we can't make that determination that it's actually an upside down 6 and a 9. So this is one major flaw with template matching theory, is it's very rigid, and it demands that all of these templates that we have stored, that the objects we're looking at in our environment match that specifically, and any changes in orientation or size or position will disrupt this process. There's also a lot of variability in templates. So for example, on the screen here, you look at the triangles, they're all triangles, but there's a lot of variability in the shape. So having a single template for all triangles is not going to work, because in the real world, they have a lot of variability in how they appear. And we also have different and unique patterns overlap with each other. So if you have a template for C, well, that's also going to be in the letter O. Same with R and P and T and I. So there's a lot of overlap and different and unique patterns, which is another weakness of template matching theory. So what are some of the key takeaways? Well, what it does is it tries to explain how the brain is identifying patterns by comparing them to pre-stored templates in memory. And while it is effective for recognizing very simple, standardized stimuli in our environment, it does not do well when we consider the variability or novelty of stimuli. So Phillips, it supports the idea that we can and do use templates to quickly recognize visual patterns under ideal conditions. same location and same orientation, but it also highlights this major flaw of template matching theory, which is the inability to account for even small variations in the position of the object. So it really just makes it impractical for recognizing real-world objects that we often see in different contexts and different orientations and sizes. We rarely see things in the same context and orientation over and over again. So major flaw with template matching theory. So we'll just quickly think about how bottom-up and top-down processing works here. So take a moment and just think about what is actually happening here. What processes are working in template matching theory. So bottom-up processing. So it primarily relies on bottom-up processes, and that the sensory input itself, so the raw data, that's directly compared to these stored templates in memory. So we're not relying on any context. We're not relying on prior knowledge, right? So if you're seeing, again, if you're seeing the letter 6 and you see it upside down, prior context and prior knowledge can tell you, oh, it's just an upside down 6. It's not a 9. But template matching theory isn't really allowing for that because all you're doing is matching that basic stimuli with a stored pattern. So it really has very limited use of top-down processing, doesn't account for how we use context, memory, expectations to recognize it when the template isn't an exact match. All right, so that's template matching theory. Now we will discuss feature detection theory. So what is it? What is feature detection theory? So feature detection theory, this suggests that the brain is actually breaking down objects into individual features, so lines and shapes, and that it's processing these basic elements in order to recognize the object. So it's not a whole template we're matching it to, we're breaking it down into individual components, each little feature of the object that we're trying to perceive. So rather than matching an object to a full template, the brain detects the defining features and then reassembles them into a recognizable pattern. So again, you can kind of stop and think a little bit about this. Do you think the brain, is this efficient? Is this not efficient? Is this a good way to perceive things in the environment? Do you think this is something that our brains would evolve to do? Does it make sense to do this? When we think about cognition and perception in the brain, one of the ways the brain has evolved is to do extraordinarily complex things in the most simple manner possible. So when you think about what the brain does, it is extraordinary. It does the most astounding things, but it has evolved to do them in what seem very simple ways for efficiency, because the brain requires a lot of energy to function. So the brain's always trying to do things in the most parsimonious way possible, or the simplest way possible. It seems simple, it's extraordinarily complex, but it's always trying to sort of streamline things, if you will. All right, so let's take a look at this here. Let's use feature detection on the cat here. So rather than matching this cat to a stored cat template, as we would do according to template matching theory, what we're doing here is we're going to get its defining features. So what are some of the defining features of the cat here? Well, it has paws, has legs and paws, has a tail, has a cat nose, has whiskers, cat ears. Would this be a good representation of a cat? Is this sort of a prototypical cat or not? Would these features work well, do you think, in identifying this as a cat? Maybe. I mean, it's pretty big. It's a huge cat. It's a massive cat. But maybe they work. But that's what we're doing with, according to feature detection theory, is we're looking at all the distinctive features and using those to determine what this is. So what are the steps and how this is actually occurring? So step one is the brain detects simple features, edges, angles, and lines from the sensory input. It's then combining them. It's combining all of these basic features to create a complete perception of the object. So recognizing the letter A by detecting the features, the two diagonal lines and the horizontal bar. So it starts at the very bottom up and builds it up feature by feature. So again, with the cat, you would start with the very basic features, the lines, orientations, and all the little shapes, and then build that up into the final picture of the cat. So there is evidence for feature detection theory, as there was evidence for template matching theory, though major flaws. So there is neurobiological evidence for feature detection theory. So if you think back to our last lecture, we talked about simple cells. Those are the ones that code for a specific orientation of a bar. There's literature suggesting that feature detection theory works by doing this. And this was work by Hubel and Wiesel. It's a number of studies. They did a lot of work on this, 60s and 70s, and they discovered that neurons in the visual cortex that respond to specific features such as lines at specific angles and orientations. So when I talked about the simple cells and the complex cells, rest, that's where a lot of this comes from, is this early work where they found these cells. They also found the complex cells that detect more complex features like movement or length of lines. And they do support the idea that the brain processes visual stimuli by breaking them down first into the simple components before we recognize it as a whole object. So this is an image from one of the Hubel and Wiesel experiments. This is a human brain. Their work was on cats, unfortunately. But here's a human brain, and what we're highlighting here is the occipital lobe. So this is where vision is being processed. But what they did was they did the work in cats, so that should be a cat brain, but that's okay. So their experiments were these experiments were conducted to explore how the brain, again, processes visual information, and they found what they called feature detectors in the visual cortex. And what we have on the image here is a simplified model of how the neurons in the visual cortex respond to different visual inputs. We won't worry about this too much for quiz purposes. We'll walk through it, but don't worry about the fine details here for test purposes. But the green bars here, these represent the different orientations of lines or edges that individual neurons, which we will call here simple cells, respond to. And that each neuron in the visual cortex, each neuron responds to specific orientation of lines. So some cells might respond to vertical lines, others to diagonal lines, some respond to horizontal lines, and that this orientation-specific response is fundamental to how we process and detect features or objects. And the reason we have these columns here is the visual cortex is organized into a columnar structure. So each column represents, each column itself responds to lines or edges in a particular orientation. Again, as indicated by the green bars. And it lets the brain process complex visual information by breaking it down into simple features, like detecting edges at different angles. So in a nutshell, we have specific cells that code to specific orientations, specific, so different lines and orientations. And it is breaking down everything we're looking at into these specific features before building it up as a whole. So some more work on feature detection is from Gibson, who proposed that objects, including letters, again, are recognized based off critical features. So When I say critical features, what I'm talking about are the important features in identifying. And these are distinctive elements or characteristics that set one object apart from another. So for example, when we're looking at letters, the brain is using these critical features to differentiate between similar looking letters. So not all features are going to be critical. Critical features are just the ones that really help us identify or differentiate between objects. Okay, so Gibson also noted that the critical features for each object, again, they'll be present in some members of the set, but not others, which is important that it's providing contrast. We need a contrast between objects, and that these critical features are the ones providing that contrast. And that the important features, so the critical features in each object, must remain unchanged under changes in brightness, size, and perspective. So when we think about template matching theory, that was one of the major flaws here, was that they didn't. So the templates didn't stay the same under different contexts, where Gibson is saying that within feature detection, these critical features have to stay the same. So no matter what changes may occur to the object, the critical features have to remain unchanged. So in our R, we have different colors, different sizes, but the critical features are still there and still the same. Same thing with a face. Even though the face is changing what it looks like, the critical features are all still there. And also, each critical feature must yield a unique pattern. So each letter has its own unique pattern of critical features. Kind of a lot here. It's kind of a lot of stuff. And that the number of proposed features should be reasonably small. So each object is going to have critical features, but not a ton of them. And that they must remain the same, irregardless of context and so on. So a lot of qualifiers here. So what are some of the strengths of feature detection theory? It's efficient. You know, the brain can recognize objects based on a limited set of these key features, and it makes recognition more efficient. So if we're not worrying about everything, if we're just looking at an object, picking out some key features, and then using those to build up the stimuli, it's rather efficient, or more efficient than if we're just using every single element of the object to identify it. It is more flexible, so unlike our template matching theory, it can handle variations in the size of the object, the context, and it does so by focusing on just these core features. And there is some neuroscience support that shows that we do have cells that respond, again, to specific orientations of these features. So it does have neurobiological support. Some limitations, however, are that it does struggle to explain how these features actually form to combine a whole object. So it doesn't fully explain how we recognize a face as a whole object rather than just a collection of these features. So it's limited there. It can't quite tell us why we're actually seeing this whole feature rather than just a collection of smaller features. And it doesn't really account for the influence of context or prior knowledge in recognizing objects that we know occurs in top-down processing. So it's purely bottom-up, where it's not accounting for using our prior knowledge to identify objects. And as happens oftentimes features are ambiguous or incomplete, and it struggles to explain how we still can recognize objects. So if we have an object we're trying to identify, but the critical features are obscured, how is it that we can still identify it? Feature detection theory fails or is limited in explaining that. So how does it make use of bottom-up first, top-down processing? Well, as we discussed, it relies heavily on bottom-up processing. So as involving the brain, analyzing the sensory data by breaking it down into each specific feature, identifying the critical features, to identify the object. The top-down processing here, this is not really part of the theory. This would be expanding on it by suggesting that in order to identify it as a whole, we would use top-down processing. So while the theory itself does not account for how we identify objects when it's unclear or ambiguous, it's likely that top-down processing is helping in that. We just don't know, or the feature or the theory does not account for how. So it doesn't get into that, doesn't explain how top-down processing is occurring, but it must be in some form to actually identify objects when the features are obscured and we can't actually extract them. Okay, so that's two of our theories down. We now have our third theory of pattern recognition, which is recognition by components theories. Okay, so what is it? I'll be referring to this RBC. So it's a mouthful. So RBC, it was first proposed by Irving Biederman in '87, and it attempts to explain how we recognize objects, and that we're doing so by breaking them down into geons, which are basic 3D shapes. So feature detection theory says we're breaking objects down into each basic feature, with critical features being the more important ones. Biederman suggests that we're actually using something called geons. So we're breaking objects down into these and using these to extract what the object is. So again, instead of relying on templates, instead of relying on features, it says that we're identifying objects by recognizing their components and how they're arranged. So let's get into that. So geons, let's just define geons. They're volumetric features that are used to represent objects for recognition. So here we have geons. And so they're all different shapes, and that these form to combine features. So for a telephone, you would use a number 5 geon, you would use a number 1 geon, and you'd have a 3 geon. And that by combining these, we can form objects, or that we do form objects. And that what we're doing essentially is breaking down objects into these geons and using those to identify the object. And Biederman proposed that there's roughly 35 simple geons, simple volumes, and that by using these 35, we can identify every object in the world. So there's 35 different geons, and that we can use these geons and combine them to form every object in the world. So how is this specifically working? So step 1 is our brains detecting edges and intersections of objects. So that's the first part. We're not doing the geons first. We're looking for edges and intersections. So we're looking for where objects are actually combining. So our briefcase here, we would first look at the outline. We'd look at where different parts are connecting to each other. So distinguishing the separate geons from each other. And then once we do that, once we identify the intersections and the edges of the objects, we then identify the geons. So we would identify the edges of the briefcase, where it connects to the other part, and then we identify the geons that are making up this briefcase. And then, as you can imagine, step 3, we assemble the geons to form a whole object. So what do you think that is on your screen? Take a moment, look at that, and try and figure out what that is. Now, I'm going to show you the exact same image, but with just different features of it visible. Okay, so it's the same thing, we just have different parts of it visible. Is it easier to identify this object than the first one? Or this image rather than the first one? It's likely that it is. So this comes from one of Biedermann's experiments, where he took an object, so in this case a coffee cup, and removed 65% of the contour from it. So each of these coffee cups has 65% of the contours removed, just different ones. And on the left, the contour was removed from the middles of it, allowing us to see how the segments were related. And on the right, it was removed from the vertices so that you would have difficulty recognizing how the segments were related. So they each have the exact same amount of information. It's just on the left, we're still allowed to see the contour. We're still allowed to see how each segment relates to each other. Where on the right, we can't. We can't see how they relate. And what Biedermann found was that participants it was actually close to 70% better at recognizing the object if presented with the observable relations versus without. So what does this suggest? Well, it suggests that the relationships between the features are very important for pattern recognition. So feature detection theory would say that we're just getting the features, we're getting the critical features, and then using those to build up, in this case, our coffee cup. But what Biedermann is saying is that, well, no, it's actually just as important that we understand the relationship between the features. So that this is critical too, is how they're related, not just what they are. So some strengths. What are some strengths of RBC theory? Well, it allows for pretty efficient recognition, fast, efficient recognition of objects, because it's breaking down very complex objects into what are simple, manageable shapes, these geons. And another strength is that we can recognize them from different angles, which makes it very versatile and adaptable in real-world situations. So, unlike template matching theory, you don't have to have the object in the exact same orientation every time. You can change angles around as long as we can understand the connection between the different angles and the geons. The angles don't matter. We can still pull out the geons and reassemble the object. And it's also very effective when objects are partially occluded or incomplete, as long as enough geons are visible. So this is another advantage over feature detection, where feature detection theory kind of breaks down when those critical features are occluded. Recognition by components theory it sort of improves over that by suggesting that as long as enough geons are visible, we can still make sense of it. What constitutes enough geons? Well, Biedermann removed 65%, so he left 35%. So that's up for debate, but as long as enough are visible. And our limitations. What are our limitations here? Well, it does struggle with fine grain recognition. So if objects are very similar, which makes sense because if they have the same geons, how do we determine differences between them? So if we're using just these geons to build up the structure and they're very similar, how do we tell them apart? So that's one weakness of RBC theory. And some objects are just very complex and detailed, and it's difficult to break them down into these simple geons. So in these cases, it would be far less effective. And again, it doesn't really account for the role of top-down processing and prior knowledge. So we're seeing that as kind of a trend here in our theories, is that these are bottom-up theories, basically. And they don't specify the role of top-down processing, which we know is critical in pattern recognition and identifying objects. So what is our bottom-up versus top-down? In RBC, well, as the others, it's primarily bottom-up because it's focusing on these geons and then combining them. And again, I mean, top-down processing is going to play a role. RBC doesn't really specify that role, but it must be playing a role in identifying things faster when we don't have enough geons to build it up. We're going to be using top-down processing. So I think it's safe to say that when using these theories, when either for feature detection or RBC, when we don't have enough features, if we don't have enough geons to build it up, top-down processing is going to come into play, and we're going to use our prior knowledge or experience or what we think the object should be to fill in those gaps and identify it. Sort of like you did with a coffee cup. So you didn't have enough information. So was it the geons you were using to build it up? Maybe. Was it top-down knowledge? Understanding of what a coffee cup looks like? Maybe. It's important to know too, if you didn't know what a coffee cup looks like, then you would have it wouldn't matter. You wouldn't be able to do it without the full set of geons. So I just put together this little table here, just of our theories, the key process of what it's doing, whether it's bottom up or top down. So they're all basically bottom up with a little bit of top down processing. All right, so that's it for today's lecture, a little bit shorter than our last couple. And yeah, so that's really about it. So we now have a good understanding of sensation and perception and how that works to let us perceive the environment. We have a good grasp on bottom-up versus top-down processing and how both of those are working and work in conjunction to allow us to identify objects in the environment and navigate our world. And we've talked about 3 of the main theories for pattern recognition. So we have a good grasp now on pattern recognition, what it is, how it works, what are the different theories. And I should note too here, I don't mean to bash these theories. It's incredibly difficult to come up with any kind of theory. So there's a tremendous amount of work that went into all of these, and they're brilliant and make a lot of sense. Trying to actually compose a coherent theory for how anything works in cognition, pattern recognition, anything, is a lifetime's worth of work. So all the authors and scientists who did this work are really extraordinary and have helped us a great deal in understanding how all of this works. So yeah, so that's it for this lecture. This is all building us up for our next section, which is going to be on attention, which is one of my favorite topics. It's my second favorite next to memory. It's a fascinating subject. It seems like a really simple thing, attention, but it's deceptively simple. It's actually very complicated. So we're going to use what we know now about sensation and perception, what we know about pattern recognition. We're going to use all of that to lead into our next discussion on attention. And that's about it. So as always, questions, concerns, issues, reach out, let me know. And I hope you all have a good rest of the week. And that's about it. Take care.